Okay. Thank you to be here also for the lecture of today. As I told you last time, I don't want to go in depth in the variation of MPC. If you want to proceed with MPC, I will give you eventually this software, which I didn't discuss directly, but believe me, at least the variations which I presented are variations which can be applied in a very easy way. But I will send you eventually the two software which I didn't present, because really is just some formal changes, which I nevertheless explain. Do you remember? This is the variation with delta U. Inside this variation, also the presence of the disturbance, how we can compensate, or better to say, cancel the disturbance. We have seen theoretically, let me say, with the solutions, where the solution come from, but I didn't simulate. I simulate just one, let me say, structure. But believe me, the variations also in the software is a few variations. Nevertheless, the software which I presented related to the first structure of MPC allows nevertheless to compensate the disturbance, because the MPC consists of nevertheless in the feature. Of course, the compensation is not exactly as in the case dedicated to the disturbance, but and the case dedicated to the disturbance is, if you remember, we have the hypothesis that the disturbance is constant through over the prediction of control horizon. This is not a conservative assumption, because very often we have a relatively short horizons. Very often also the sample time is very short. Sometimes happens that the dynamics of the systems after controlling or the pre-controlling is very fast, and the disturbance does not change much in this context yet. But we have to know the disturbance. The disturbance cannot be known. This means must be estimated. For instance, Kalman filter. This means to apply this method of OMPC, which includes the disturbance, is not so cheap. It's expensive in terms of calculation load, in terms of implementation in general. But again, if you decide to go ahead with this variations, I have a software to give you. At this moment in my study, I think this indeed should be present the variation of this is the basic variation, which nevertheless compensates the disturbance. But of course, we need very large Q. Last time this I did. A very large Q implies very large inputs. Of course, method more dedicated to the presence, to the rejection, or to to handle with the disturbance, in this sense is cheaper in the sense that we can use let me say, more optimized input. Because do you remember, in the cost function we have states, error, and inputs. Error, let me say, and inputs, better to say, but the error depends on the states, of course. Input is an external signal which came from the controller. Of course, this also depends on the input in somehow when we close the loop. And in this sense, if you have the disturbance, we need a very high input to compensate. With the variation dedicated to the disturbance, of course, we pay the price to implement a more complex control structure, which include again the observer. But of course, in terms of input, we have some advantages. The advantage is that the amplitude of the input is less than the variation which I presented in detail with the simulation. Today, a new topic. Before starting next week again, we will meet to tell you about, I would like to tell you about Lagrange method, because in economics it's relatively important. Today, we will consider the optimization of trajectories. Why this topic is the a natural topic to be considered after introducing the MPC. Because we have seen last time, but in general, the problem of control is to control the system in a working point, but more in general, we have to take the system around the trajectory. Trajectory could be not necessarily a kinematic trajectory, in a movement. Trajectory means a profile to be tracked. Also in chemical systems, economical system, which we don't have exactly a movement of an object, but we have a movement of capitals. We have a movement of investments. I would like to track my money in the bank. I would have to obtain the money in the bank. We change over time, we increase over time $1 million per year. We can think about this trajectory to be tracked. Today 0, next year 1 million, after next year 2 million, and so on. We can imagine that we have a profile of what money over time. This means trajectory is a very wide concept, which means movements, which means how the states, about the state I told you a lot, no? Change over time. Nevertheless, today I will present a trajectory which is a movement of a mass of a car, because it's more natural, or in general for engineers. But believe me, but it's easy to understand. Trajectory in control, but in general, in track problems, the tracks problem involve control. It could be every changes of states. Could be money over time, could be as money, liability, assets over time. Could be also some concentrations in some chemical reactions. Could be also population profile in COVID, starting from I don't know 1 million infected people. We want to decrease this amount of infected people each year. I don't know what we were decreasing, and then we have to consider a campaign of vaccination input from a model predictive control. It could be a nice project, which realize this. This means we have a trajectory to be tracked. And the idea is to calculate and you that realize this goal, which track this my goals over time. But of course, the problem which occurs is how is the best trajectory? This is a problem which, in general, is a difficult problem. Just thinking about, which involves also the control strategy. They are connected, definitive. They are connected. We will see now today in which sense. Think about if I want to decrease the infected people tomorrow, I don't know, from 1,000 to 0, let me say to 0. Of course, in one day, I have to organize a campaign of vaccination extremely strong. This means I have to have at disposition structures, not only structure, doctors that is which allow to do this vaccination. Anyway, everything which I need to realize this goal. This means it could be that I don't have this structure. Or let me do an example in engineers. If I want to obtain the velocity, if I want to change the velocity from 0 to 100 km per hour in 1 second, of course, I need the power, an input. It could be not feasible for the system. This means also the choice of the goal of the trajectory in this sense makes sense to consider an optimization in the context of what I want to obtain and in which time. Trajectory, because trajectory means my goal over time. In the context of MPC makes sense, because we have seen that you have a trajectory to be tracked. We have seen just the trajectory in the context of a motor. This wasn't a real motor, but you know that we can consider trajectory also in economics. Okay, let me show you the first slide. It's a shame I didn't find a slide in God bless you. I know that is not so, should be better in, let me see if I'm able to, nevertheless, to hold the lecture with this material, because I am so stupid that I didn't find, yeah, but I think we can work with this. I think we can work with this. Look at this example here. It's a kinematic trajectory, in a kinematic problem, better to say. Because in my opinion, could be better understood. But again, this kind of problem can be seen in any kind of dynamical system. Look at this problem here. I have to travel from Lüneburg to Hamburg. Hanover, excuse me. Doesn't matter, no? That is, anyway, we have a goal. It matters, but it's not important for us. This example, in my opinion, didactically is more effective than if I consider a variation of concentrations of, I don't know what, with respect to the time, because we can imagine what happens with the car which is moving. If I consider the variation of the concentration of chemical substance over time, is a little bit more abstract, in my opinion. Anyway, here it's quite easy to see that the idea is to travel from Lüneburg to Hanover, starting from the time Ti input, initial, I don't know what, and Tf final. This is the problem, and I mean the context. And let me now formulate a little bit the problem. Assuming that Ti and Tf are given, not necessarily both are given. Could be also the object of the optimization problem. Let me see at this moment to understand Ti today, excuse me, although I was in the night, but today, at this time, let me say more or less 9:06, we are starting to traveling, and Tf is the final time which I would like to reach Hanover within 1 hour. This means Tf is 10:06, and Ti is 9:06, 1 hour, for instance, no? The difference in between. We can see here, this is the difference. Time of the travel is given. Let me consider this, let me say, problem which is easier than to consider one Tf free. We will see what I intend for free. This is more easy to understand. I would like to reach Hanover from here within 1 hour. Let me, before formulating the problem, let me consider the model of the problem. The model of the system, the sense, this is the model of the, which I will consider in this optimization problem. Let me consider an easy in the sense, linear. I told you about this concept of the linear, non-linear. But in any case, linear means basically that I can use the superposition principle. This means in the equations, we have a linear combinations of the states. This means no products between the states, no product between states and the net input, no state square, not root of states. Anyway, we can formally define what a linear system is, but probably you have in mind from math. No product, no square between the states, not product between input and states. And the linear combination, let me say, of input and states. Look at this, more concrete. It's more easy to explain than to explain the model than to, at least in this context here, than to try to define with words the linearity. Look, the derivative of x equal v, in which x the position of my object, the car, for instance. And the second equation is known. The second equation is the Newton balance, which we have the mass multiplied the acceleration in terms of v derivative equal the sum of the forces include, the forces which play a role in the system. We will see which one in 1 second. I don't know if you remember last time, no? X derivative, v derivative, basically the changes of the states represent the change of the energy. Again, also here, let me say protagonist is the energy. And if you remember in high school, when we are speaking about energies, we are speaking about changes. V is the velocity and the state which reflects the kinetic energy. X is the position which reflects the work. Work is also energy. The sum of Fi, we can see here, in this system here, we'll consider the motoric force F. I didn't write, here, motoric force. Fi is the, as I told you, the force is acting on the car. I will consider here two forces. Again, the motoric force, which is at the end, we will see something which must be calculated to achieve under some conditions, Hanover, the conditions is, for instance, 1 hour at this moment. And we will see not only 1 hour, but to minimize, for instance, the consumes. I try to introduce element which I will clarify a little bit later. But of course, f of t is something which could be calculated. Then the friction force is, in this context, linear. The friction force, which depends on the velocity, we know it depends on kV, is in a constant, extremely difficult to be calculated because depends. Anyway, in this case, I am considering just an object without dimensions. The friction force depends in a car from the shape of the car. If you look at Ferrari, I think last week Ferrari won. Ferrari won last week. I don't remember. Yeah. I don't remember. I heard. I don't care about Ferrari. Even though Ferrari comes from my country, no? Close to where I where I grew up. But I don't have Ferrari. I don't like. As an object without dimension, this means really is an ideal. It's really the didactic example. And kV is a parameter which concentrate, let me say, in one point, this effect. Of course, it's an extremely strong simplification. If you want, we concentrate also friction due, rolling friction of the wheel, everything which is against. You can see this minus here, the velocity, the movement somehow. The velocity states the movement. Physical constant. Here's the model again, in the form which we know, which is the model again, in the form which we know. The derivative on the left of the states, position and velocity, equals, as a function of states and input, or input in our case. We can see here. Here we have the state, here we have states and input. Yeah, the boundary constraint, we say, we use the word in order to classify, to include in the problem, the constraints, or let me say, our desired, which in the context of the language of optimization, we call constraints, the time, let me say, position and time. Look here, at time T1 could be zero. T1 could be zero when we start, but could be any kind of time. Very important is the difference between TF and TI or T. Yeah, TI. No, I called at the beginning TI. It seems to be T1. It does not matter. The initial time equals xi or x1, which is Lüneburg. Could be also this zero as a reference. Do you remember in high school when we start, we consider zero because our reference in time, for instance, also in the position. Let me see. Here is the time zero, T1. X1 is Lüneburg. Could be also zero, our reference. Lüneburg is in a word, but in the context of mathematical context, in the context of a software, we cannot write Lüneburg, because we have to translate this concept of Lüneburg is a value, zero, this means, for instance. But could be also 10. If Lüneburg is 10 kilometers, this means that the reference is not Lüneburg. It's 10 kilometers far away. XTF is the position. ETF is the final time between TF and TI is 1 hour. I told you, and XF is 100 kilometers, for instance. If XI is 0, if XI is 10, XF is 110. Assuming that the distance to be covered is 100. Look, I will add, for instance, we will see later why I am defining so, and where in which different form I can define this kind of problem. I would like to introduce also two other constraints. Must be, we will discuss a little bit in a few minutes. But let me consider this problem here. I consider two limitations, two condition in position and two condition in velocity. It seems to be that at Lüneburg, the velocity equal x1, xi derivative, and in Hanover, x is xf derivative. Of course, I can consider also the velocity 0, the beginning, starting from 0, and I can consider that xf dot is 0. This means exactly at this time, I would like to stop in Hanover, but not necessary. I don't know if it's clear. This is a very important thing in the practical application. It's easy to understand. I try to repeat nevertheless. I am in Lüneburg, xi. I am in a time ti. I would like to be in Hanover at time tf. But the question is, I can include eventually also desired velocity in Lüneburg and desired velocity in Hanover. In particular, is in Hanover, because if I start from Lüneburg, not necessary, but we can consider 0, but not necessary, because I am considering also the problem in which I am passing through Lüneburg. And when I passing through Lüneburg, I switch on my cruise control system, MPC control, in which I calculated with this intelligent unit in the car, the optimal trajectory to achieve Hanover within 1 hour. Achieve Hanover means not necessary to stop in Hanover. In this case, the velocity in Hanover is 0. Means also pass it through. This means could be any value, x1 dot, any value, so xf dot. To complete the optimization problem in this context here, I introduce here the cost function. About the cost function, we have seen in MPC what is the meaning. The cost function is a function which should be minimized and is basically one of our goals, not a unique one. Here we have these boundary conditions which represent nevertheless our goal. The goal is to reach Hanover, starting from Lüneburg. First goal. Second goal, with particular velocity, in particular in ANOVA. Is in ANOVA the specification, basically. Because when I am in Lüneburg, I know the velocity. This means the specification is just in this sense in ANOVA. And considering this cost function, what I am saying with this cost function? Do you remember the product between the force and the velocity is the power, is the mechanical power. I am considering as a goal the integral of this mechanical power, which represents the mechanical energy. I don't know if you remember in high school, the integral, or in some courses here, the integral of the mechanical power represents the mechanical energy between, in our context, in our problem, Lüneburg and Hanover, Ti and Tf. Ti and Tf. This means I'm considering to minimize, not only to reach from Lüneburg, Hanover within 1 hour within a specified velocity in Hanover, assuming that is given the velocity in Lüneburg. But also, I would like to minimize the mechanical energy. Why the mechanical energy and not the gasoline? Because in the problem which I define using these two equations, I didn't consider any variable which reflect directly the gasoline. I mean, we have a mechanical system. The states, again about the states. The states are position and velocity. I don't have any chemical element which reflects the gasoline. This means I can just minimize in this, consider this model, mechanical cost function. But nevertheless, this mechanical cost function reflects indirectly the consumption of gasoline. Because it's the power, mechanical power, which I need to achieve within 1 hour, within Tf minus Ti, Hanover. With the minimal, if I would like to consider the minimal J, now we will see with respect to what? No? Reflect the consumption of gasoline. At this moment, I didn't tell you what is the variable which I would like to calculate as to minimize this J function, but it's intuitive. It's intuitive. Let me open the second slide. Second. It's intuitive because the idea let me see, it could be that I can tell you before let me tell you this. Before going in depth on the optimization problem, let me do some consideration again, even though you know, because about the convexity, I already told you. Let me tell you some notation, then we will go in depth on the optimization problem. Anyway, at this moment, I define the model which we need. You remember, MPC also needs a model. We need, in any case, the cost function to be optimized always in the optimization problem. And here I introduce a little bit more in detail the constraint. Constraint is our condition, which nevertheless represent our goal somehow. Let me go through some notation and then we will reconsider again in detail what we want to minimize. Yeah, as I told you, model, cost function, boundary conditions. This kind of problem, the name of this kind of problem is an optimization problem. Let me say two boundaries, very often is the name, points optimization problem, because basically we have 2 points, the initial point and the final point. Therefore, two boundary point optimization problem. About the convexity, I don't need to tell you, again, two boundary point optimization problem. I don't need to tell you this trivial example. Is convex the optimization problem because we have a linear model, as I told you last time, and we have a cost function which is quadratic in this sense, in a convex function in this sense. Convex function, linear model, even though with boundary conditions. Boundary condition does not mean inequality, because if we have inequality, the problem remains with a linear model, with a quadratic function, for instance, or the convex cost function remains convex. But it's a shame we need a solver. But with boundary condition, with equality, we can calculate analytically the solution. This I told you last time. Let me skip this because you already know. Two boundary point optimization problem I already told you. I give you some values. It could be that I have time to, I don't know, to show you the software. Otherwise, I will upload exactly with this example. This is the cost function which I already defined. Let me go ahead a little bit quickly. About the mechanical energy, I already told you. Now, again, indirectly, to minimize 3 means to minimize the consumption of the travel. But of course, indirectly, because the chemical aspect, the gasoline, is not present in terms of state. We have just mechanical aspects. Now, let me go in depth in the optimization problem to calculate the trajectory. The goal is to calculate the trajectory. Now, look at this expression here. X of t is our trajectory. Trajectory means, again, position over time. It means, if I do the derivative, velocity over time. This means I would like to calculate the profile of the velocity. Do you remember the lecture of last time in which we track the velocity with MPC? But I didn't tell you how I obtained this velocity, where this comes from. I told you this is the velocity to be tracked. Now, with this example, we can understand how we can, for instance, is one method, it's not the unique one. But at least I would like to give you idea how we can optimize the profile to be tracked. It doesn't matter if it's in the velocity, it doesn't matter if it's in chemical concentration and so on, because in control, not only in control, in general, is a very important optimization problem. And if you remember the lecture of last time, it's extremely connected with the track. Because last time I told you, this is the velocity to be tracked. Without saying, that is good, what is bad, this velocity. If it's good, why is good? What good means with respect to what? Yeah, with respect to an minimization of course, the model, it was a little bit more complex. It's an electrical system with 2 states, a velocity and a current. I have also somewhere also, yes, a more complex model in which we have not only the point which is moving with the mass, of course. I consider also something like an electrical car. It could be that I have a time to show you. In any case, in general, how I can design this trajectory. Look, at this moment, I am considering this trajectory, and if you do the derivative, I have the velocity, which could be the velocity, for instance, is not exactly the same of last time, because last time I didn't put 2 points to be reached. Anyway, it was a little bit easier, the problem. But let me come back on this specific problem. Nevertheless, I will obtain here and a trajectory at the end. Why I am considering a trajectory which depends of the time? This could be easy to understood because the trajectory depends of the time. My travel plan, X is my travel plan, which implies the velocity. Why we have a polynomial of second order, first of all? It's an interesting question. Let me take the slides. Let me share. Yeah, we can see, as I told you, if now we will see why this choice. If the position is represented by this equation here, the velocity is represented by this equation because of the derivative. No? And in accordance with the model, I can calculate the expression of f of t, no? Because I have the model, which is this one. I can explicit the model with respect to f of t. This means, assuming that x of t is this one, assuming the sense x of t, we have a v of t. This one, I can calculate f of t. At the end, I will calculate also the optimal f, which allows to achieve an offer within 1 hour, for instance. You remember 3,600 seconds. If you look at the data which I wrote at the beginning, with the minimal, let me say, kinetic energy, consumption in this sense, no? In terms of mechanical energy. Why, before doing the calculations, this choice? This can be seen from here. To understand, let me probably, excuse me, I forgot. Yeah, now it's better. Yeah. Why I am considering this curve? We can see that this curves depend on 3 parameters, A0, A1, A2. Once I calculated A0, A1, A2, I have the trajectory. This means the optimization problem is a consistent optimization problem if I'm able to calculate A1, A0, A1, A2. Let me say univocally, or at least if exists in general, will be not only one solution, and then we have to verify which is the best. When we have more than one solution, we have more than one solution if the problem is not convex. You remember this, I told you. And then if I have 2 solutions, I have to verify which one guarantees my boundary condition, and in particular, which one guarantees the minimal J. But I already told you that this problem is the convex one. I explained also why. This means we are waiting for A0, A1, A2, unique one value for A0, one value for A1, one value for A2. Let me go ahead practically to show you why it is enough. This is the polynomial of the second order. Look, assuming that Lüneburg is our reference, this means Lüneburg represents xi, it is 0. 0 at time 0. This means if I consider here in the equation in the first, let me see, where is? In this equation here, x of t equals 0 because our reference, it works for any kind of value. No? If I put 10, it will work, but a little bit, I don't want to say complicated, but you have to do the calculation. Assuming that Lüneburg is our reference. I start with the, with my reference exactly at Lüneburg. 0 equal times 0, because I can consider also times 0, A2 equals 0. Clear, no? We can see here. Exactly the first boundary condition implies A2 equals 0. Look now at the second boundary condition. Xf, this is in our case 100 kilometer, we can express everything in meter, equals, look at the first equation again, A0 multiplied Tf, which is 1 hour, this means 3,600 seconds square, plus A1 multiplied 3,600 seconds. A0 is 0, therefore I didn't put here. This means I can calculate from, where is it? Yeah, from this equation, A1 is a function of A0. I mean, xf is given, tf is given, A1 is the function of A0. This means if I plug in this expression A1 in the velocity, which is here, the second equation, A1 is the function of A0, I will end up in this equation here. V, it seems to be, is a linear function with respect to the A0. Let me say, isn't it bilinear in the sense depends of t and depends of A0, but very important for us is A0, because once I calculated A0, I have the optimal velocity. I have the optimal velocity to be tracked, for instance, with model predictive control. I don't know if it's clear what I want to intend. Here, I cannot include the condition on the velocity at Hanover, because if I fix the velocity at Hanover, I will fix also the A0. This means this original problem which I presented, in which I try to introduce also the condition, the velocity, cannot be solved with a polynomial of order 2. I mean, in accordance to what I am doing here, it seems to be that the problem can be solved just if I have the condition on the Lüneburg position, initial position, in the sense, and final position, without putting condition on the velocity. Why that? Because mathematically, we have here just one, we need just a parameter to optimize the trajectory. But if I put some other conditions, particular one condition, more than one, I cannot. I will fix A0. But if I fix A0, what is the optimization? It's fixed. This means the original problem can be solved, but I have to consider a polynomial higher order. I mean, it's easy to see, if I have a polynomial of the second order, I can fix just two conditions, position Lüneburg and position Hanover. And then with the free element which I have, A0 in this case, but could be also A1, we have nevertheless a free element. This can be used to optimize. This means if I desire more conditions, of course, I have to increase the order of the polynomial. To sum up, considering this polynomial here, I can consider just two conditions. Position Lüneburg, when I started, this is necessarily to put it. And where I have to, of course, in which time, where I would like to be, but no condition the velocity. If I need a condition the velocity, I have to increase. The reason is I need always an optimization problem, at least one parameter free for the optimization. What happens if I consider the polynomial order tree in this context here with just two parameters, conditions, because position, initial position, final position. Of course, time. The time is implicit in the sense. We will end up, nevertheless, in the polynomial of second order. This could be nice also in a possible project. I mean, the element that if I add t up to 3, multiply and a constant, this constant will be automatically calculated at 0. If the condition are true. Of course, I can include another condition if I have a polynomial order 3. Let me do the calculations. Boring, but it is possible by hand because of the polynomial second order. Therefore, I did input higher order of polynomial. But I have also software already realized. Look, the idea is to minimize J. Now I will try to explain with respect to the free parameter, which is A0 in this case. But you can choose the free parameter to A1. It doesn't matter which one. I mean, now here I have A1 is in a function of A0. This means our velocity is in a function of A0. But you can calculate an equivalent form A0 in a function of A1. This means the parameter to be optimized is A1 is not A0. But yeah, once we have A0, we have also A1. And this means we have the optimal velocity. How we can calculate? The integral of what? F multiply V. F is D. Bain F, which is in a function of V and V derivative. V derivative is one. Look, I plug it in my original cost function, which is the integral between 0, in our case is Tf, of what? Here, I don't know if you see here, is the V of t. We can see exactly at the beginning, then V of t. Everything is dt, and this expression here is the force. With k multiply v, m multiply v derivative. We can see here, 1 second, m multiply v derivative, which does not depend on the time, kv, which multiply again v of t. Now, very quickly, these boring calculations, you can look at Ohm. I will be happy if you choose this topic. We can formulate interesting, some students, of course, interesting small problems inside this. Again, the goal is to calculate the velocity, which can be considered for our MPC of last time, even though last time was totally abstract. No? But you can understand that MPC can really, any kind of optimization method, in the context of track problem, I presented just MPC because, in my opinion, is one of the most important. Why is important this element, this analysis? I do very boring calculation now. This product again. The idea is to calculate A0. If I do these calculations, products, this I don't need to explain much because it's algebraic things. Let me now, I'm almost at the end. No, almost. Let me share. I don't know if I share. I don't understand. Yeah, I hope. If I do the calculations and if I do the integral, believe me, this is the integral polynomial. It's not a problem to do. We can see that I have an expression J in which everything is fixed, everything is given. What is not given is A0. Believe me, doing the product and doing the integral between 0 and TF, we will obtain an expression as a polynomial expression which depends on A0. The rest of it is given. This means we can see that the polynomial is the polynomial of second order. We can also demonstrate why. If I do the derivative of J with respect to A0, also it's a boring calculation, and I put equal 0, believe me, at the end, I will obtain this expression. This is just exercise of high school. The derivative of the polynomial of the second order with respect to A0 allows to say that we will obtain just what A0 in a parabola. We have a minimum. It's in a parabola with a coefficient A0 squared positive. This means in a convex parabola, not concave parabola. And this is the solution. This is the optimal A0. This means if I have the optimal A0, I have the optimal acceleration, because I didn't tell you, but do you remember V was 2A multiplied T? V derivative is basically the acceleration. Here I do the analysis, the unit analysis, you don't need to do that. But anyway, in order to verify that at the end we have an acceleration. This is just a technical. Let me now show you the optimal velocity. But the optimal velocity now is just to plug in. Excuse me, today without the material was this difficult so for me. Yeah, once I have A0, I use this position here, which I already explained where this comes from, to obtain A1. At the end, A1 is this expression here, and plug it in A0 and A1 in V, I have the expression of the velocity. We can see that the velocity is in a linear function with respect to the time. Acceleration I already calculated before. And of course, I can calculate also x of t, because x of t was in a function of A0, A1, A2 was 0. AX2 is in a parabola with respect to the time. And basically, I have here the acceleration, which is in the break phase, and I have here the velocity. And here it seems to be that we have the x of t. Basically, to achieve in 1 hour my goal, I have this automatically calculated this initial velocity must be this, and then I will break. I cannot, we can see here, I cannot give an initial velocity because the polynomial is too small, the order too low. We can see, in fact, the initial velocity depends on the parameter of the model M, KV, but in particular depends of KXF and TF. Because I cannot give more specifications. Of course, if I wish other constraints, I need to have more parameters. This means more complex a more complex, let me say, trajectory, the sense. Okay, I think this is the last, almost the last. Let me see if I try in these 10 minutes, if I try to show you another short presentation. Next week, you see, it seems to be have another, even though this does not tell anything. I know this is not connected. It's connected with, but I would like to tell you. I would like to tell you. It's not directly connected with the problem which I presented today, but a little bit, yes. Do you remember at the beginning of this lecture, I told you that the problem is convex. This convexity is reflected in this problem which is here. Remember, at this moment, I told you the derivative of J with respect to A0 equals 0 can be calculated analytically. But of course, not always the problem is convex. Not always the problem can be calculated, let me say, analytically. And also, if you have a convex problem in general, we cannot say, in general, when we have more than one solution for the J with respect to the A0 or with respect to something, it's just a mathematical problem. This kind of not convexity is reflected in this calculation here. The zero of the derivative, the gradient to zero, no? Or the derivative to zero. We had here the J with respect to A0 equals 0, which in our case was relatively easy to be calculated. We have just one solution. In the sense we were able to calculate. Please pay attention, even though sometimes we have a convex problem. I told you about this considering inequality instead of equality. Or think about if I consider, if I have at the end, if I consider a cost function, let me say up to 4 instead of up to 2. We have to calculate the zero of a polynomial order 3. This means we have 2 zeros. 3 zeros in this sense. 3 zeros, excuse me. This means not necessary sometimes to calculate the zero of a polynomial order 3, we need a numerical analysis, even though the original problem is convex one. Here is the method, probably you know from another course, this Newton method, which is the basic knowledge for, I would like to say, for almost all numerical methods to calculate a zero of an equation. Yeah, I would like today conclude with this. Next week, at the beginning, I will show you a more complex, it's a more complex polynomial. It could be that I need two lectures. Next week is after next week, but you can attend the class from home, no problem. I will be here because I would like to tell you a little bit about this. Could be nice because this could be also a very nice project, and also Lagrange, because as I told you, no optimization course without Lagrange, at least flesh out. Let me a few minutes to introduce in this concept the Newton method. Probably you have heard about it in some different courses. Because if you need to calculate the zero Of course, not necessarily to calculate the zero of an equation is easy. Think about a polynomial order 3. Order 2, we can calculate. Order 3, not necessarily, we need very often a numerical method, just to consider the concept. And to calculate a zero of a function, we have seen also today, the derivative of J respect to A0 equals 0. It was easy because it's didactical. But if we have something complex, even though this equation came from an optimization problem, a convex optimization problem, not easy to calculate, analytically impossible, as the function of the parameter. Today it was possible. You remember A0 was the function of the parameter. And this is the method, the Newton method, which is why this slide. Because this slide is again, the method is the most important because the basic of each optimization method. Somehow, also PSO reflected this. The difference in between reflected the derivative. Think about this, and then we can discuss together during the project. PSO basically is the gradient method based. Gradient means derivative. Gradient if I have more than one dimension. Today we have seen A0, just the derivative. But it could be that we have more than one dimension. We will see also this next week a little bit. The idea of this, look, you have a function f of x, and we have a 0 f of x here. How I can calculate this numerically? Yeah, this is the equation. This is the equation, which can be easily implemented. I have also the software if you need to calculate. Here's the solution. X recursively, X I didn't put here is this point here. Starting from xi, it doesn't matter where, left and right, apply this expression here, which came from this here, which is the approximation of the derivative. Let me explain intuitively in two words, or the three. In order to, this is the final expression, which can see that iteratively I will converge to x, which realize f of x equals 0. Applying this, it seems to be complex, but it's not. Yeah, just the definition of a convex function. Probably you remember from math. I don't need now to repeat, but we can see that this segment between x1 and x2 is always the upper part, or it's the up the curve. This means convexity, and here we have the mathematical definition. Look at this moment is not relevant. But I would like to explain this expression here, which allows numerically, because often we need the numerical solutions. We are not able to calculate analytically, even though the problem is convex. This is the approximation of the derivative. Why? If I start from it doesn't matter if left or right with respect to the point. Let me consider right, but we don't lose generality. F of x1 is this distance here. It's written here. Yeah, it's written here. Divided xi minus xi plus 1, in which xi plus 1, we can see here, represent the point in which the tangent at the point, let me say xi, f of xi, is calculated, which is exactly this. I don't know if you remember a little bit in gymnasium, in high school, what is the if f derivative of xi? This means the tangent on this point is this distance divided this distance, which represent the tangent of this angular alpha. It's just here. And if I explicit this expression with respect to xi plus 1, I have the recursivity, because xi, I put xi, it doesn't matter where, left, right, It doesn't matter how far away. Very important, nevertheless. And then why this convex function that I will put xi in the neighborhood of my point, which I have to guess where it is, which is convex. Otherwise, the convergence is not guaranteed. This means I have to know a little bit where the point is, and to be relatively close, assuming that the region in which xi is included is convex. We can understand a little bit. Then I will consider this point here, and I will consider the derivative on this point, and we can see intuitively that will converge. No, this point here is basically xi plus 2, assuming that in the interval between xi and my candidate point is monotone in the sense, convex. Otherwise, the convergence is not guaranteed. We don't have convergence, we can say. This is a necessary condition. Therefore, the method of PSO based on an extension of this with more element, very often in very complex problem, is more suitable to find also zero, no? To find also zero, or to find directly the minimum. No? I don't know if it's clear a little bit this concept here that must be convex, basically must be something like that around this point here. We can say also monotone. Let me see if I forgot something. I don't remember now, but anyway, let me conclude here. Next week, in a part of next week, I will consider a more complex problem in the contents of the trajectories with more conditions. And then we will, I don't know, probably I will show you a little bit the software very, very quickly. Then I will conclude the course probably after next week, considering the Lagrange problems. Okay, let me think at home. If I forgot to say something at the end of the lecture, I'm always a little bit confused. Yeah, we will see next week. Thank you for your attention. I'm here to discuss project and so on together. No? Message. Yeah, I am here for you. And then let me close the